This is the overall front panel for the system. Here we begin to show how the LDRs work in orienting the solar panel to adjust to following the light. LDRs 1 and 2 are responsible for the top, 3 and 4 the bottom, 1 and 3 the left, and 2 and 4 the right. Blocking off one of these pairs will make its opposing pair move towards the light. If the horizontal and vertical errors are below a certain threshold, the solar panel will stay stationary in its optimal position for solar energy harvesting. Here we have a sped up video of us testing the RTDs, where the fan and thermoelectric cooler will simultaneously turn on once the threshold of 25 degrees is reached. Here you can see 25 degrees reached and the fan and thermoelectric cooler activating. Once they cool off the RTD, the fan and thermoelectric cooler stop once again. Here we are demonstrating the functionality of the solar cell, showing that increasing light intensity both shows on the front panel and on a small LED we've attached to the solar panel for easy visual access.
Here is the circuit board for the LDRs. We have each column represents a voltage divider for each respective LDR. LDR 1, 2, 3, 4 correspond to its respective analog input channels on the DAC, 1, 2, 3, and 4. We have a common ground over here for all the LDRs. This is the circuit board for the RTDs. We have a Wheatstone bridge for increased sensitivity to measure the resistance of the RTD. We have a voltage regulator to prevent voltage spikes and capacitors to reduce noise. We also have an amplifier because the RTD changes in signal are very small and we want to be able to amplify the signal for an easy register on the lab view. And we also have the signal connecting back into channel 0 of the Quanser DAC of analog input. This last circuit board is dedicated for the actuators. The MOSFET acts as a relay for the 12 volts to come in for the fan because the fan runs on 12 volts. And then we also have a relay itself for a stable 5 volts input into the thermoelectric cooler and acts as a switch to turn it on and off so it's not constantly running. This is the VI. So here we have the HIL initialized that go into actuators, but the way that the actuators are initialized are from the RTD. Here the RTD has an output voltage that goes onto the front panel and the calibration to convert it into temperature. If the RTD temperature is above a threshold of 25 degrees, then it will send a signal through a feedback loop to constantly check this condition, and if the condition is correct, it will simultaneously activate both the thermoelectric cooler and the fan, which are digital scalar signals. And then this is separate from the thermoelectric cooler and the fan. It just automatically displays the intensity of the voltage from the solar cells. Over here we have the sensors related to the LDRs. So this is LDR 1, 2, 3, and 4 respectively. Here are the calculations to find the average for the top and the bottom LDR. So that would be 1 and 2 and 3 and 4. To create the vertical error, which is top minus bottom. The horizontal error is the left average, which is 1 and 3, and the right average, which is 2 and 4, doing left minus right for the horizontal error. These errors go into take absolute values. If these absolute values are greater than 0.3, which is experimentally determined to be a satisfying value, if they're greater than 0.3, they will execute this command. These commands are the same for the top and bottom, so I'll just go through one of them. It takes the actual non-absolute value of the horizontal error and verifies whether it is positive or negative by determining whether it is greater than 0. A positive value for the horizontal error specifically means that the light is stronger towards the left. This will move the, if this condition is true, if it is positive, it will add 2 degrees, or if it is negative, then it will subtract 2 degrees from the initial value of 90 degrees. This initial value, this is the addition statement. This initial value gets tested into a range and coerce function. If it is above 80 degrees, it cuts off. This is the limit. And then the limit for the negative section is 0 degrees. This is to make sure there's no strain on the motor. And then this output gets added and the feedback loop continues, while the output gets sent to the servo motors over here. These get sent to the servo motors, where the small servo corresponds to the vertical direction, and the big base motors correspond to the horizontal direction. And these are just the calibrations to turn these points into degrees for the HIL rights.